Now, for the exciting conclusion to yesterday's notes, where we were talking about the factor theorem and synthetic division, we finished up yesterday factoring this polynomial by using synthetic division. We showed how to use the rational root, or excuse me, the remainder theorem yesterday and the factor theorem. And today we're going to kind of bring it all together with finding rational zeros. So we have the rational zero theorem. It says if you have a polynomial, which is what you're saying here, where n is greater than or equal to 1. So if you have a polynomial and you have every coefficient being a real number that is non-negative, obviously, we're going to be using the P over Q test, which is what I was taught it was called. X equals P over Q is a rational zero of f, where P and Q have no common integer factors other than plus or minus 1. Then P is an integer factor of this number at the end, where Q would be an integer factor of the leading coefficient, P over Q. And these are all of the possible rational zeros of a polynomial. Now, are any of them guaranteed to be zeros? No. But they're the possible ones. And we could check all of them using the remainder theorem if we really, really wanted to. But what if there's a lot of them, right? I mean, I'm talking like, what if there's like 60 options? Do we really want to be checking all of them? No. So what do we do then? We use Descartes' Rule of Sine to narrow it down a little bit. It narrows it down a little. Now, it's not going to tell us these are the roots, but it will say, okay, well, there's certain patterns that are going to be possible. It is used to find real possible root combinations. It also will tell you the complex possible root combinations, but we won't talk about that one today. It says the number of positive real zeros in a polynomial function is the same or less than by an even number, meaning subtracting by 2, as the number of changes in the signs of the coefficients. So if we have a polynomial, like this one down here, you just look at the symbols and you ask yourself how many times did it change sign, and that is the possible number of positive real zeros, or 2 less than that number, or 4 less than that number, so on and so forth. The number of negative real zeros that are possible is found by evaluating f of negative x, and then counting the sign changes again, and then again, it's going to come down by an even number. It's kind of weird to say it in words. Much easier to show it with mathematics. So here we have a cubic. And first thing we're going to do is we're going to talk about P over Q for this one. And remember, P is the integer factors of the constant at the end, and Q is the integer factors of the leading coefficient. So we look at this number at the end, which happens to be positive 1. It has 2 integer factors, positive and negative 1. Those are the only factors of this number right here. And since our leading coefficient is 1, its integer factors are also just plus or minus 1. So this is a very easy question, designed that way on purpose. It only has 2 possible rational roots. Those 2 possible rational roots are positive and negative 1. That doesn't guarantee that one of them is a root. Those are just the only possible rational roots. It could have irrational roots, and that's what we're getting at. Now, this is a cubic. We know it crosses the x-axis. It doesn't have a choice because one end up, one end down. So yeah, it crosses the x-axis at least once, but it's not guaranteed that that happens at a rational answer. So let's see. So 1 and negative 1 are possible rational roots. Now let's use Descartes' Rule of Sine to see what our options are. And we're going to look at, let's see, What did I called it R for some reason in my notes. Rational, I guess, is what I was going for. But let's look at, oh, I know what I was doing, R for remainder. I want to use Descartes' rule of sine here first, just because I mentioned it already. And I'm going to count the number of sign changes. Let's see. So for f of x, I have, this is positive, this is negative. There's a sign change. This is negative, this is positive. Oh, there's two sign changes. So f of x has two sign changes. So that tells us the number of possible positive real zeros is either 2 or none, because you have to come down by 2 each time. So this is possible positives. Two or 0. And let's see what f of negative x is. Okay, we're going to actually find f of negative x. Anywhere that you have an odd exponent, you know you're going to have a sign change because it's an odd number of negative numbers. So here, when I evaluate for negative x, this is negative x to the third power, which gives me negative x to the third. Now here, because I have an even exponent, plugging in a negative x is not going to do anything, because negative x times negative x is just x squared still. So we have minus 3x squared plus 1. Then we would count the sign changes we have here. Here's one from here to here, negative, positive. That is a single sign change. That means there's 1, or no, you don't have an option because you can't subtract 2 from 1. So possible negative real roots is 1. It's almost as if it's guaranteed that I have a negative real root. That's what that implies. Doesn't mean it's rational, but we do know that we have a negative real root. All right, so what do we do? What I would do is I would use the remainder theorem, and I would check my possible rational zeros using the remainder theorem. And if I get a remainder of 0, I found a root. Does that make sense? And if I check the remainder theorem and I don't get 0, that's not a root. So let us see. Remainder theorem. Our remainder, when we're checking positive 1, remember that just means evaluate the polynomial at the number, is going to be 1 to the third minus 3 times 1 squared plus 1. So 1 minus 3 plus 1. Yeah, no, I'm just plugging in positive 1. I'm checking f of 1.
Yeah, but like at the beginning, like it says negative.
Oh, no, that's when we were using Descartes' rule of sine. The original polynomial is what we're checking.
Oh.
Yeah. This is just to see how many possible negative real roots there are. Since I can't subtract 2 from this, basically we've been guaranteed that there is one negative real root. We've been guaranteed that. So there's either going to be 2 positive real roots, which would give us our 3 roots, or there's going to be no positive real roots, which would imply that this thing only crosses the x-axis one time. We're going to see which one we get. And actually, we don't even know if we're going to have any rationals. Let's see. 1 minus 3 plus 1? Yeah, that's negative 1. Okay. Yeah, x equals 1 is not a rational 0 because we got a remainder. Let's check the other one. Fingers crossed that it works. And we're just going to evaluate for negative 1 in our original f of x. So we have negative 1 to the third power minus 3 times negative 1 squared plus 1. All right. Negative 1 to the third is negative 1. Negative 1 squared is just 1. So minus 3 plus 1. Oh my goodness. Look at that. The rational root theorem only gave us two possible rational roots. Now, like I said, it's a cubic. We know it crosses the x-axis. Anything with an odd power has to cross the x-axis because one end up and one end down. But that doesn't mean it has to do it in pretty places. Rational root theorem gave us two possible rational roots. The remainder theorem pooed on both of those numbers. So what does that mean? Since, let me pick a different color. Purple feels good. Since both have remainders, oh, I forgot my D. Since both have remainders, neither options are zeros. Let's say x-intercepts. I'll put in parentheses zeros. Bless you. So what does that tell us? Even though we know that this cubic has to cross the x-axis, and we know it crosses the x-axis at least one time on the negative axis, it doesn't have any rational zeros. That means the places where it crosses the x-axis are irrational. And my nerd brain's not going to let it go. I want to know where this thing crosses the x-axis, at least whether or not it's positive or negative. Grab handy dandy grapher. Obviously, when you're home, if you don't have your graphing calculator, or if you don't own a graphing calculator, you could just use Desmos. Let's get the glare off the screen. There we go. The last time I used this calculator was yesterday, and I believe I was in parametric mode yesterday. Click mode. Yep. Scroll down to function. Alrighty, let's see. Let's clear the old stuff out of there. X to the third minus 3x squared plus 1. Now remember, Descartes' Rule of Sine is telling us that there should be one negative real root. So we expect this graph to cross the x-axis to the left of x equals 0. Zoom 6. Whoa, look at that. So it did cross the x-axis 3 times. Guaranteed that one of them was going to be a negative 0, and the other two were positive. And that does add up to 3. So cool. It works. They're just irrational, which means we can't really factor this thing. What do you think? Not too bad, right? Yes? No? Maybe so? Yeah, Damien, what's up?
Where'd you, for the P and Q thing, where'd you get the ones?
The P and the Q thing. Okay, let me go ahead and clear this off. P is going to represent all of the integer factors of this number at the end.
What do you mean all the factors? Just like
Well, if I said this number at the end was a 12, then numbers that you can divide 12 by, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. So you have to give me all of the positive or negative numbers that you could divide the constant at the end by. And Q is all the numbers, positive or negative, that you could divide the leading coefficient by. This one just also happens to be a 1. Okay? Good with that? Now, I do know that it's a little confusing because P comes before Q in the alphabet, but for some reason P is the factors of the end, where Q is the factors of the beginning. I know. I don't know why that is that way. I'm not going to lie. I honestly don't know. You just have to do your best to remember that it's a little bit backwards. Okay?
wait, what does it mean? It says like so 1 and negative 1 are possible rational.
Rational means something that can be written as a fraction. Doesn't repeat decimals. It doesn't go on forever. For example, 1/3. This is a rational number because it can be written as a fraction. Right? The only possible rational roots that this thing has, meaning places where it crosses the x-axis, are positive 1 and negative 1. Now, you saw the graph. It crossed the x-axis 3 times. What happened was all 3 of those zeros are horribly irrational numbers, which means we don't have a way of factoring this polynomial. That's what that tells us. Okay? And it'll make more sense when we do another example, one that actually has rational roots and things like that. So here we have the polynomial 3x to the third plus 4x squared minus 5x minus 2. This thing is a degree 3 polynomial. That is an odd degree polynomial that guarantees it has at least one real zero. It doesn't mean it has to be rational like you just saw in the last example, but it does guarantee it crosses the x-axis at least once. But because it is a degree 3 polynomial, it could cross the x-axis up to 3 times like the last one did. Cool. So what do we do first? Well, I would try p over q first, just to figure out what my possible combinations are going to look like. Then I would use Descartes' Rule of Sine, then the remainder theorem. That's always my process. I set up my p over q's. I then use Descartes' Rule of Sine just to see possible combinations. Then I start checking using the remainder theorem. The remainder theorem is our friend. It's a shortcut. It shows us what things we should be using. Cool. Let's switch colors. So, tell you what. P is going to be found by this area. Whoops. And Q, by the way, P is not negative 2. P is just coming from the area of negative 2. And Q is coming from this region, the leading coefficient. So we're going to do P over Q. And we are going to be looking for all of the factors, integer factors, positive and negative, of P and Q. So the number at the end is negative 2. All of the integers, positive and negative, that I could divide negative 2 by, plus or minus 1, which, by the way, is always an option, and plus or minus 2. Comfortable so far? Our polynomial's leading coefficient is 3. Plus or minus 1. Like I said, plus or minus 1 is always an option. And since 3 is prime, plus or minus 3. Awesome. So what is that telling us? I'm not going to write them all. I'll just go ahead and tell you what all of your possible rational roots are. Plus or minus 1. Plus or minus 1/3. Plus or minus 2. Plus or minus 2/3. Those are all of your options. So plus or minus 1, plus or minus 2, plus or minus 1/3, plus or minus 2/3. That is 8 possible rational roots. 8 possibles. Okay, now let's do Descartes' Rule of Sine. Let's count sign changes. So for f of x, let's count how many sign changes. Positive to positive, that's not 1. Positive to negative, that's 1. Negative to negative, no. So f of x has 1 sign change. That is going to guarantee us that it has 1 positive real root. It doesn't have to be rational, but it does have 1 positive real root because I can't subtract 2 from that. Then we have to count the sign changes on f of negative x, and oh, you know what would be helpful is if I could see f of negative x. So let's see, I'll fire that bad boy right up here. Let's get f of negative x. Remember, what we're doing here is just evaluating for negative x, so anything that has an odd exponent, sign changes. Anything that has an even exponent, nothing happens. Odd exponent here, sign will change. Negative 3x to the third. Even exponent here, nothing's going to change. Exponent here is a 1, which is odd. Sign will change. This doesn't have an x, so it is unaffected. Let's count up our sign changes now. Negative to positive, there's one. No. Positive, negative, there's another. F of negative x has 2 sign changes. What does that tell us? That tells us that we have 2 or 0, because I can subtract 2 from 2, 2 or 0 negative real roots. Again, they don't have to be rational, but they would be real. So let's see. How do I want to write that? Do I want to write in words? Tell you what, how about I start setting up a grid thing that Miss Klein likes and therefore I like, and it will be on our test. The structure will look like this. Using Descartes' Rule of Sine, we'll list out all the possible combinations of positive, negative, real roots. So positives, there's 1. Okay, that was simple enough. For negatives, we either have 2 or we have 0. You guys cool with that idea? Yes, ma'am. Why do we subtract the 2? The reason why is because roots will come in pairs often. Okay, I don't want to let the cat out of the bag too much because it's part of the next lesson. So the next lesson describes why this happens. I'll just go ahead and I'll tell you why we subtract 2 if possible. And by the way, let's say this number had been a 5. Then it would have been 5 or 3 or 1. See, we're going down by 2 each time. Now this one I can't go down by 2 because
So what if it was 3?
if it was 3, then it would be 3 or 1. You just keep subtracting 1. Here's why. So I'm going to cheat a little bit and I'll tell you what's going to happen coming up in the future. This polynomial has to have 3 zeros, but they don't all have to be real. And if they're not real, that makes the other zeros complex. That doesn't mean it's crossing the x-axis. Obviously, a complex 0 can't be graphed in the real number plane, but it is still technically one of its solutions. And complex solutions always come in pairs. So because they come in pairs, it forces us to subtract by 2 on our real options if we can. So people don't normally ask why that early, but I'm okay with it.
I didn't know why you were doing that.
Yeah, well now you know why.
Okay.
It kind of takes the punchline away from tomorrow's notes, but that's okay. I don't mind. But that's why we're subtracting 2 if we can. So yeah, it has to add up to 3. So if you either have all 3 are real, because we know there's 1 positive, but if there was 0 negatives, then it would guarantee us that we have 2 complex roots, because it has to add up to 3. So your combinations would be 1 positive, 2 negative, which would mean no complex. 1 positive, no negative, which would then mean 2 complex, because that we're going to add a 3rd row to this very soon. You looked into the crystal ball. Okay, but there you go. All right, what do we do? I'll tell you what I do. I use remainder theorem at this point to try to be lazy. I'm going to be real. I'm trying to be lazy. I always hope that positive 1 or negative 1, one of them, is one of my zeros. And if neither one of those works, then I would check positive 1 or positive 2. I would basically check my integer values first because I really don't want to have to evaluate fractions. I just be honest with you, that's what I do. I always check all the possible integer values first because I don't want to have to evaluate at a fraction. And I will tell you, I was kind to you when I chose your homework questions. Okay? They weren't blind blind choices. I was kind. Yes, ma'am. Was that a question or just no? Oh, okay, sorry. All right, so let's go ahead and check some stuff. Let's check f of positive 1. Let's use the remainder theorem and check positive 1. Our remainder when we check positive 1 is 3 times 1 cubed plus 4 times 1 squared minus 5 times 1 minus 2. Let us see. 3 plus 4 minus 5 minus 2. Hey! Jackpot! That worked. Was that an accident? Of course not. You know, it makes for fast notes. Mr. M, I'm doing my homework, and it's not as easy as the one you did in the notes. What happens when I check f of 1 and I don't get 0? Then move on to f of negative 1. And then just keep going, checking through your integer rational roots until you do find a 0 using the remainder theorem. That's what you do. This worked. What does that tell us? That tells us that x minus 1, because remember this was a 0, x minus 1 is a factor of this. This is a cubic. If I were to divide it by x minus 1, my result would be a quadratic, correct? From yesterday's math, when we were doing synthetic division stuff? One of the factors of this polynomial must be x minus 1. If we divide this by x minus 1 using long division, we will get a quadratic. Or we could just use synthetic division to figure out what our quadratic would be faster. That's what we're going to do. Now that we've established that we know one, oops, I'm pointing at the wrong place. Now that I've established that I know one of my real roots, I'm going to use synthetic division to see what's left over. My coefficients of f of x are 3, 4, negative 5, negative 2. Make sure you're not missing anything. X to the third, x to the 2, x to the 1, x to the 0. All right, nothing's missing. Remember, if you're missing an x term, it needs a 0 filler. Okay, so we have 3, 4, negative 5, negative 2. And we are trying to use synthetic division. Guess what? I already know what the remainder is going to be. It's going to be 0 because the remainder theorem said so. You start your synthetic division by dropping down that first number. We have a 3. And I like to do synthetic division with addition. Technicolor mathematics here. Alrighty, 1 times 3, 3. Add straight down. 4 plus 3 is 7. 1 times 7, 7. Add straight down. And, yep, synthetic division confirms. 1 times 2 is 2, and negative 2 plus 2 is 0. This is the quadratic 3x squared plus 7x plus 2. What does that mean? What that means is if you had done the long division, you would have gotten a statement like this. Your f of x, which was that cubic at the top, is 3x squared plus 7x plus 2 times x minus 1. That's what we've established so far. One of our solutions is x equals positive 1. The other two possible solutions, which, by the way, are either both negative or complex because no negative, are going to come from this quadratic. We solve quadratics either using the quadratic formula, if we're forced to, or by factoring. Yeah, I mean, I prefer to factor when I can. So I would check first and foremost to see if it factors. 3 times 2 is 6. Are there two numbers that multiply to 6 that add to 7? There is. Fantastic. That means I can avoid the quadratic formula and I can go directly to factoring. And that will give me an opportunity to review the Lizzie method as well. So we're hunting for two numbers that multiply to a times c. Our a times 3c is 3 times 2, which is 6. And we need those two numbers to add to our b value, which is 7. And what are the two numbers that multiply to 6 and add to 7?
6 and 1.
6 and 1. There it is. Cool. That means our quadratic, remember that's what we're factoring at this point, our quadratic, which is right here, instantly factors to two sets of parentheses. X belongs in the front of both of them. At this point, we're trying to figure out where this thing equals 0. X belongs in the front of both of them. Both of these values are positive, so plus, plus, and both of these values belong over our a value, which is what makes this the Lizzie method. So both of these numbers over a. 1 over 6 over a was 3. Six over 3 is 2. And we can now see our other two solutions. Our other two solutions are x equals negative 1/3, which was one of my possible rational roots, and x equals negative 2, which, yes, was one of my possible rational roots. And from what we discovered in our remainder theorem, 1 is the third solution. So it did have the 2 negative real roots and the 1 positive real root. Ta-da! Now when you get to your quadratic, will they always factor? No. And when they don't factor, that just means their roots are not rational, and the rational root theorem would not have found them. You'll have to use the quadratic formula. What questions can I answer about this process? It's a little frightening that there are no questions.
I got it.
You got it?
Yeah.
Okay. Well then, oh yes, what can I do for you?
When you said that the homework will be kind, do you mean it'll be like this and we won't have to continuously just like check few and few?
So when I say that I was kind with the homework, I'm guaranteed that the ones I chose have at least one integer root. And I'm pretty sure I stuck to cubics, which means once you find that integer root, what's left over is a quadratic, and it'll either factor or use the quadratic formula. Yeah, I have no reason to beat you guys up. Is that it? All right.